Now let's look at the common base amplifier configuration. The input is applied to the emitter and the output is taken at the collector. The base, which is shorted, forms the common terminal between the input and output ports, hence the name common base. So which model do we use to analyze this circuit? The hybrid pi model would work just fine, but notice that our sig is going to come in series with the emitter terminal, so we can employ the T model. Now let me make some changes to this diagram and incorporate the small signal equivalent circuit with the appropriate conditions. Here we are, and we have labeled the base, emitter and collector terminals so that you can know which parts have been replaced by what. Now notice that RC and RL are in parallel. Why? Because CC2 has been assumed to be short-circuited. We again analyze this in the same way that we did the common emitter amplifiers, and we start with Rin. As you can see, it is simply Re. This is because the other terminal of Re is connected via base to the ground. We substitute for the emitter current and we obtain the voltage gain V0 over Vi. This expression, except for its positive sign, is identical to the expression for AV for the common emitter amplifier. Rout, as you can also see, is simply RC. We can also calculate the overall voltage gain. Here we are, and we notice that the voltage gain is almost independent of the value of beta, which is a very desirable property. Now let's derive a new quantity. This is the short circuit current gain, AIS. Let me define it this way. The ratio of the output current to the input current under the condition that the load resistance is shorted. So this is very easy to find. When the load resistance is shorted, we are simply connecting V0 to the ground. So writing the expressions for I0 and II with alpha IE and IE both flowing from collector downwards to the emitter, we get this expression minus alpha IE divided by minus IE. Now this reduces to just alpha, whose value is close to 1. Now this is a very useful property. This amplifier is also known as a unity gain current amplifier. Another name for it is the current buffer. The buffer means that an input current taken at low resistance is delivered at an almost equal value at a very high resistance. You can see that Rin is very low and Rout is very high, while the short circuit current gain AIS is almost equal to unity. And this is a very desirable property. Now the small input resistance Re causes severe attenuation at the input of the amplifier. The gain is given by Re divided by Re plus Rsig. Now, until and unless Rsig and Re are comparable, you are going to have severe attenuation, as only a very small part of Vsig is going to appear across Ri. One of the applications of the common base circuit is to amplify high frequency signals that appear on a coaxial cable. To prevent this problem of attenuation, the common base amplifier is required to have an input resistance equal to the characteristic resistance of the cable. This is usually between 50 to 75 ohms. To understand this more fully, let's do a numerical together. Here we are. You have to design a common base amplifier for signal delivered by a 50 ohm coaxial cable. Amplifier should provide proper termination for the cable and an overall voltage gain of 100 volts per volt. Find IE, the DC bias current, and the total resistance in the collector circuit. Now you might have noticed that there is a very limited space on the screen. But the thing is, this is a very simple numerical, so I don't need much space to solve it. Let's start. First notice that Re equals 50 ohms. Because of this, R6 should be equal to Re, And we have a formula for GM equals IC over VT. Now, we don't know GM, neither do we know IC. So how is that going to help us find IE? We do, however, know RE, and we know the relationship between GM and RE. So we divide the equation for GM by alpha. This gives us 1 over RE equals IE over VT. Now, using that we can calculate IE because RE and VT, thermal voltage, are both known to us. And the answer comes out to be 0.5 milliamperes. As for the total resistance in the collector, that is also easy. We are given the GV, which is the overall voltage gain, as 100 volts per volt. Multiplying GM with RE gives us alpha, and alpha is usually equal to 1. So the total resistance in the collector, which is RC parallel with RL, is automatically gifted to us. The answer comes out to be 10 kilo ohms with the value of alpha taken to be 1. Now, reading the wording of this question may have frightened some of you, but in fact it is a very simple numerical.